Good evening, everyone. I'll just quickly start off with my own introduction. I'm Shailesh, and I'm one of the team leads currently at AI Club in IIT Madras. So I won't be taking a lot of time explaining what I'm going to present right now. The session is based on CNN, but I'll take some 10 minutes to explain the assignments for the next two sessions. So I hope my screen is visible. So we are slightly deviating from the previous ones where we used to give you guys Google Forms and ask you to code out stuff or answer questions. So as you can see on screen, we are gonna conduct a hackathon for you guys. So hackathon is basically a competition, a machine learning competition which will span across some 4 to 5 days. I'll quickly run through you about the platform and stuff. So this website is known as Kaggle. First thing first, you'll have to log in onto Kaggle using a Google account, or you can create an account on Kaggle itself. That's up to you. No issues there. So Kaggle is a website where most of the major machine learning competitions happen throughout the year. Some are monetary, some are non-monetary, and it's also a very good platform for you guys to get your hands dirty and participate in these competitions and get a good hang of your coding skills and how to implement data pre-processing, etc., etc. So for a beginner level, like this is a hackathon which we have prepared for you guys. And this will start off by tonight 8 p.m. and it will end on Sunday night. I think it's 4 days for that. So I'll run you through what to do in this website, then you can play around with the data yourself. So overview, it will show you the overview of the competition, the description, what is this about, like how your scores will be evaluated, etc., etc. Coming to the data, like this is the most important one, obviously. On the right hand side, you can see three types of data. One is test, one is train, and one is sample summation. So you'll have to download all three of these so that you can do data pre-processing and model training. So coming to the train data, you have some 14 features over here. I'll select all. You have 14 features called passenger ID, home planet, cryosleep, cabin, destination, age, VIP, room service, food court, shopping mall. Like these are all expenditures spent at these particular locations. And at the end, you can see a column called transported. So transport, in the sense that this is a hackathon where spaceship kind of crashes and you have to predict whether the person is, transported to another dimension. So if it's true, you have to predict it's true. If it's false, you have to predict it's false. So this is a training data set. And again, you'll have to do data pre-processing, like we had taught you guys in the second session, different types of data pre-processing, how to fill in empty values, look for trends, etc., etc. That's all up to you guys. And then after training a model on that, again, this binary classification problem. So you'll have to implement models which have been taught to you guys, ensembling methods, whatever. It's up to you. And then after train your model, you have to test it on this data set. You have to download the test CSV, and then you have to test it on that. And if you look closely over here, just a minute, this does not have the predicted value, like the test data set. Obviously, it won't have the true and false over here, and that's something you have to do. With this model, you have to predict either it's true or it's false. And after that, you'll have to submit it. So sample summation looks like this. So every passenger will have a passenger ID that will be given in the test data set. So in front of that, you just have to, get the predictions out, and you have to create two columns, one for passenger ID and one for true and false. That's all. I would recommend you do one thing. You just download the sample summation, get your true and false values after you run the model on the test data set, and just copy paste over here. That's all. Fine. And then when the hackathon starts, there will be an option over here that will be called submit predictions. So on each day, I think you can submit up to 5 predictions. That is, you can tune your model, or you can change the type of data pre-processing you're doing if you feel that this is not working pretty well, or there's a better way for approaching this problem statement. You can modify your code, you can modify your data pre-processing methods, get a new set of predictions, and then you can submit it again. So essentially, I have a total of 20 submissions from today to Sunday night. So you'll have to do that. And again, this will be a running leaderboard. Like you can see other people, what they have done. You can't see their codes though, but you can see their scores. You can see the accuracy. Score is basically the accuracy, number of correct predictions divided by the number of total predictions over there. That's all. Fine. So this would cover like pretty much everything that has been taught till now in the summer school, right from Python to data pre-processing to regression, classification, and clustering, etc., etc. Whatever has been taught till now, you can implement whatever you want over here. You have been given full freedom to implement, get your hands dirty, and push for the top spot. And again, attempting this hackathon is compulsory. You won't get any assignments from now. You won't get an assignment today or after the NLP session. So you'll have to do this. Like this will be considered as an assignment for this session, next session, and the past session. Fine. And it gives you absolute amazing amount of freedom. You can look through, like again, whatever we have taught a very small chunk of ML till now. You have absolute freedom to look into wherever you want, whatever you want. And then you can, let's see who gets for top spot. So people who are asking where it will be held on Kaggle itself. That's why I'm showing this platform. Like this, you won't need to like go to Google Forms or any other website. You just go to Kaggle. We'll share you the link of this hackathon. You just have to join the competition. That's all. It's completely free, of course, nothing else. Create an account on Kaggle, join the competition. You will get all the data over here. Again, I'll run through it. Download all this data and then use this data on whatever platform you prefer for coding. Either it can be Google Colab, and also one more thing. Just a minute. Kaggle itself has an option to code. So if you go to new notebook here, you can actually code with a notebook which will come over here. Yeah, just a minute. Yes. So you can even code over here, or you can even download the data set and load it on your local machine, say VS Code or something. So I hope that's clear. So I'll just check the chat. So yeah, that's all from my side. So this competition, it will go live at 8 p.m. today. We'll share you the link. You have 4 days, and just I think you can create. And also, if you want, you can create teams among yourself. That's also an option over here. You can create a team of 10 if you know your friends who are also in summer school and would like to. Can use TensorFlow for it, sure. I mean, we didn't teach TensorFlow. We taught you guys PyTorch, but if you guys know TensorFlow, it's well and good. You can use it. But looking at the problem statement, I don't think you will require TensorFlow. But up to you guys. You can also create a team of up to 10 people. But if you create a team, the number of submissions still remains the same. Like you can't be like, I'm creating a team of 10, so I'll get 50 submissions. No. For every team, there is only a fixed number of submissions. You can go through the rules. I'll repeat again, this is compulsory for everyone for certification, because this is a replacement for your assignments for the past one session and the next session. We won't be giving any Google Form assignments from now on. Okay, I'll just go through it once just to give a final clarity. Kaggle is the platform which we'll be using for the hackathon. Log in with a Google account, or you can even create an account on Kaggle itself. We'll send you the hackathon link. Just click on it, join the competition. You download the data from over here, the train, test, and sample summation. The train data is which you'll be using to train your model. There are like 13 features over here, like 13 input parameters. And the 14th row column has the target data. That is either it's true or it's false. You have to predict if the value is true or is it false. That's it. Fine. And then after train the model, you go to test. You upload this to your whatever platform you're using. Test this data set with your model, and then you predict the true and false, because there's no true and false here, of course, because it's test data set. You predict the true and false, and then what you do is you go to sample summation. Sample summation will have passenger IDs, and just you have to state them in front of them. Is it true or is it false? The test data will have their passenger ID, so you can use that also. And then when the hackathon is live, over here you will get an option of submit predictions. So you have to create a CSV file for your test like predictions, and you have to submit it over there. That's all. And after the submit, it will take some 1 minute to evaluate, and it will show up over here if the submission is successful. If it's not successful, then it will show an error over there, and you can debug the error on your own. Maybe like it's not matching the number of test items are there, or the true and false values are not matching, etc. That and all will show over there. That's not an issue. Yes, whatever we have taught is well and sufficient. If you want, you can just revise the concept which you have taught till now. But whatever has been taught is well and good sufficient. You don't need anything extra apart from whatever we have taught. It's not compulsory to have a team. You can go solo also, no issues. If you know your friends, you can form a team, but it's completely fair to do it single. I guess that's it. If there are any more queries regarding the hackathon after it goes live at 8 p.m., just put it on the group. We'll help you guys through the entire process. I'll hand it over to Anish, who will be taking today's session on CNNs. Over to you, Anish. That's it from my side.
So, hi everyone. Welcome to the penultimate session of AI Club Summer School. And today we'll be covering convolutional neural network. In the previous session, you guys got some sort of an intro to CNNs, and now we'll be building upon to it. But of course, I'll start with a recap of what we did in the previous session because it's pretty important. So let's get started. So firstly, the question comes, why do we need CNNs? Why can't we just process images using a regular neural network? So let me come to its flaws. So firstly, let's assume that we have a huge data set of O's and X's, and we need to classify them into an O or an X. So, and we need to do it using a regular neural network. So here's what we do. And we're also assuming that there are 36 pixels in the image. So here's what we do. Basically, we'll consider each pixel to be the input node, which is basically like the first layer of a neural network. And using this, there'll be weights and biases allotted, and then we'll classify it into O and X in the last layer, mostly through a sigmoid or a softmax. So this is what is done. But then there are some problems. The first one being that since it has 36 pixels, there are going to be 36 nodes in the input layer. And since there are 36 nodes in the input layer, there are going to be 36 weights per node in hidden layer. So like, as you can see, it's going to get computationally expensive. Let's say in the hidden layer, I'm going to have like 200 plus nodes. So the total number of weights becomes, like 36 into 256, like assuming I have 256 nodes in the hidden layer. And if I have multiple hidden layers, it just keeps getting bigger. All that makes it computationally expensive. So I'll just give a small recap on what I said all this time. Basically, when you use each pixel as an input node, there are too many learnable parameters, which leads to a lower accuracy. So assuming each of the input node will be connected to each node of the hidden layer, if we assume a hidden layer of 256 nodes, we need 256 into 36, which is 9216 weights. So like this was a hypothetical example, of course, but let's assume you're going to use the MNIST database. You must have come across the MNIST database in one of the previous sessions. So we'll be considering the one in which there are handwritten numbers. And these handwritten numbers have a dimension of 16 cross 16, which makes it 256 input nodes. So let's say the first hidden layer just has 36 nodes. We still get 9216 weights. And usually there'll be more number of nodes and more hidden layers as well. So End of the day, it takes too much time. There are too many learnable parameters, and more than time, you'll get a lower accuracy as well. There is another problem in using regular neural networks for image processing. The thing about images are pixels which are close together usually have similar values. Well, like maybe it might not be clearly visible here. Like, in fact, it is visible here. You can see the white pixels have a lot of white pixels surrounding them, and the black pixels are also connected to the other black pixels. Generally, in any image, you can see this kind of a pattern, unless it's just randomly generated pixels. So when you use a regular neural network, you're not utilizing this property of images. But in CNNs, we are doing that. In CNNs, we are not just giving an individual weight for each pixel. We are rather trying to find out what pattern is there. So what this does is, it makes sure, like, even if the image is slightly displaced to the left, right, or even up or down, it will still classify it correctly. However, in an artificial neural network, it's likely that this right side image will be given a different label compared to the one in the left. So, like, summarizing this, in a regular neural network, each of the 36 pixels will have its own weight and they'll have a common bias. However, in this is not going to be the case in a CNN. In CNN, there'll be a new term called as a kernel, which will have lesser parameters that have to be learned. We'll get to that in a moment. So yeah, before starting upon CNNs, there are some important terms that we need to know so that we'll be able to do examples. So let's just see some terms. So yeah, in the first term is, of course, convolution. It's there in the name of CNNs itself. So all you need to know about it is that it's a mathematical operation which is very similar to dot products. It's pretty simple. When we do an example, you'll get to know. It's basically, you need to, in dot product, you basically multiply the corresponding elements and then sum it up. That's what you do here in some way. We'll come to that in a while. The second term is going to be stride. So if you recall from the previous lecture, stride is basically the leap the kernel takes while doing the operation. The kernel is basically this 3x3 cell that you see here. And as you can see, it moves towards the right, and then it goes down, right again, down, and then right. And each time it moves, it takes a step of one cell. I mean, initially it was in the first to third row and first to third column. And then it goes to second to fourth column and first to third row. So the step is one. So that is what the stride is. You can see similarly when it goes down as well, it just moves by one row. So that's the stride. Stride can be 2, 3, it can be anything. It's up to us. It's a hyperparameter. We will define it. Yeah, so just a recap of that. Convolution between two functions in mathematics produces a third function expressing how the shape of one function is modified by other. This is a very bookish definition. Like, when you see an example, you'll see that it's actually way easier than whatever is mentioned here. Stride is just what step the kernel moves. For example, a stride of 1 makes a kernel slide by 1 row / column at a time. And a stride of 2 moves a kernel by 2 rows / column at a time. Kernel. A kernel is a small 2D matrix whose contents are based upon the operations to be performed. So in case of a CNN, the values which are there in the kernel, like let's say it's a 3x3 matrix, the 9 elements which are going to be there will be learned, basically. That's it. Kind of is corresponding to a weight in a regular neural network. I hope I'm not going too fast. You can just put any doubts in the chat. If you have any doubts, you can just put it in the chat. So yeah, another term in CNNs is padding. Someone has asked, explain convolution again. Yeah, we'll get to convolution. Honestly, I haven't explained it in depth yet. We'll come to that in a moment. So yeah, another term is, of course, padding. So you might have thought about it in one of the previous slides. Here you can see that it perfectly starts in the first column, and then in the third around, it kind of ends in the last column, which is the fifth column in this case. However, in some cases, if the stride was, let's say, too big or some random number, it's possible that the kernel kind of goes outside the image. Basically, the kernel doesn't have any value to take a dot product. So to avoid this is what we do, the process called padding. Padding is just we add an extra layer along both, I mean, at the top, bottom, left, and right. It's a layer of zeros. I mean, if it's zeros, then it's called zero padding. And it's normally zeros itself because we don't want to introduce new terms over there. And padding is also a hyperparameter which has to be set by you during execution of the code. So here are some kernels. Like these are not the kernels which are exactly used in CNNs. These are usually used in image processing. So let's just see some kernels. Like this is an original image kernel. So this is very intuitive to understand. So as you run this through an image, it's like the new image is just going to be the same pixel because all the surrounding pixels have no weightage because it's all just zero. But only the middle pixel is one. So only the middle pixel is going to be returned. Like here in the padded example, you can imagine. So like I guess you can see my pointer. It's kind of on this middle cell. So only this value is going to be counted in the new image because I mean, this is anyways zero, but then either way in this, all the surrounding elements have the value zero. So moving on to the second type of kernel, it's the Gaussian blur. And most of you might have come across Gaussian blur in your mobile phone, but you might not have explicitly known that it is Gaussian blur. So like Gaussian blur is, of course, it's a blurring kernel. What it does is it gives more weightage to the pixel and the weightage slowly decreases as you move away. Like the corner pixels have one and the side pixels have two. So Gaussian blur is mainly used to reduce the noise in an image. It makes sure that the essential features in an image are remaining, while like there isn't too much of a difference between surrounding pixels. This is also like pretty intuitive if you see it from a blur point of view. It's like almost similar to an average, but there are different weightages like for different pixels. Some more kernels can be sharpen and edge detection. This might not be as intuitive as the first two. So yeah, let's just see how the images look. So here I have just some images. I've performed some image operations and I've put a picture. And all these kernel operations were just done using CV2 module in Python. You can also use Octave, which is kind of ideal for performing such operations. So here you can see this is the original image. And after I applied the Gaussian blur, you can see here, it's kind of blur and you can say there's lesser amount of difference between surrounding pixels because it's somewhat of an average. So this image is kind of ideal because it has lesser noise. And some more kernels, sharpened kernel, this is edge detection, Gaussian noise, black and white, this is an inverted image and this is contrast. So I just, you know that the original kernel is nothing but 000, 010, 000. I mean, it was just done in the previous slide over here. So, I mean, this should be kind of intuitive. Can you guess what the kernel for the inverted image would be? So, like you will have to answer it. It's a Slido question. You guys can just scan it and just try answering. The question will appear once you scan it, of course, but I'll just repeat it. It's just, you just need to understand what the inversion kernel is going to be like. I'll just share my Slido screen. I hope you can see the screen. It's related to the inverted kernel. So yeah, I can see people have started responding. I'll show the results like maybe in a minute. I'll just give you time to think. It's very similar to the original image kernel. I mean, you can somewhat say it's the opposite of that. That's a hint. I'll just wait for a minute or maybe 30 seconds. Yeah, so we've gotten like about 55 responses. And yeah, that's enough amount of time for this question. So yeah, the answer is indeed -1. It's just going to be same as the original image kernel, but the one is going to be -1 rather than +1. I mean, it's pretty intuitive to understand. Like another possible assumption you might have made, which would be wrong, is it would be a 3x3 matrix with all the elements as -1. But then that would be similar to an averaging function because you're kind of you're giving weightage to surrounding pixels. But yeah, this kernel is just going to be 0, 0, 0, 0, -1, 0, and again 0, 0, 0. So move on to the next concept. I'll just go back to the presentation screen. So yeah, once again, here's an illustration of the kernel movement. This is of course in 2D. It first goes along the row and then down the column and then again along the row and then down the column till it reaches the end of the image. And the leap is also called as a stride, depends on how many rows or column it skips in each movement. So yeah, someone was asking about convolution. So here's an example. You can see this. So we're assuming this is the kernel while this entire thing is the image. It has 16 pixels here. So as I said earlier, convolution is essentially just dot product. What happens here is this. You multiply the corresponding elements in both the 3x3 cell from the input matrix and the kernel. So what is it in this case? It is 45 into 0, 12 into -1, 5 into 0, 22 into -1, 10 into 5, 35 into -1, 0 into 88, 26 into -1, and 51 into 0. And this results in the top left cell of the output image. So that is -45. Similarly, this 12 would be a result of this square. You can see the mouse movement, I hope. It's basically from columns 2 to 4 and row 1 to 3. Meanwhile, this 22 will come from the bottom 3 columns and the first 3 rows. And the 10 will come from the bottom 3 columns and the right side 3 rows. This is basically just the contrast kernel. And yeah, if you're interested, you can just try it out yourself and verify if this is the result. So I just hope you understood what exactly happens in a convolution. It's just dot product and then addition. It's way more simpler than matrix multiplication. I hope you'll agree with me on that. So, I mean, I can stop for doubts. If you have any doubts, you can put them in the chat, or else I'll just move on to the next topic. So you would have noticed that in this case, the input matrix had a 4x4 dimension, while the kernel had 3x3. The stride was, of course, 1. And in the end, you got a 2 cross 2 matrix. So you might be wondering, is there some mathematical relation that will relate all these parameters? Well, yes, there is. So there is a simple formula which relates the dimensions of the output activation map as a function of the input channel dimension, stride, padding, and kernel size. So this is the formula. N out is equal to N in plus 2p minus k by s plus 1. You might have seen this in the previous session as well. I'm just reiterating this. N out cross N out would be the dimensions of the resulting matrix. N in cross N in would be the dimensions of the input matrix, or let's say the image. K is nothing but the kernel dimensions. It'll be K cross K. P is the padding if it is used, which is just the extra zeros which is added. While S is the stride. In the previous case, S was 1. So yeah, that's how we get it. And of course, there's a plus 1 at the end. So this is a pretty simple formula. You can remember it if you want. So that pretty much covers all the basics of what you need to know about CNN. So now we'll get into a CNN architecture, what it generally consists of. So yeah, so a CNN consists of 3 main things, which is a convolutional layer, a pooling layer, and a fully connected layer. A convolutional layer is where the convolutional operations happen. You might have seen it. And pooling layer, will come to pooling in a little bit. And the third layer is a fully connected layer. And a fully connected layer is just a regular neural network. It's a fancy word maybe for a regular neural network. I mean, for classification, we do need to apply the softmax. So leading to that, there will be a few hidden layers. So that's what this is. So let's learn each layer in detail. So in convolutional layer. So what happens here is we apply the kernel, we add bias, if any, and then we pass the output through an activation layer. You might remember the word activation layer from one of the previous sessions. And the activation layer we'll be using mainly is ReLU. I hope you guys know what ReLU means. So let's just take an example of what happens over here. This is the input image, and this is the kernel. We can say that maybe the kernel, we did backpropagation, and this is what was learned. And this is maybe we're just testing the image, and we'll just see what's happening. So now what happens is we'll be going through, the entire convolution. The stride is most likely just 1. We'll apply it throughout the image, and we'll basically we'll basically get this as the output vector. So if you want, you can try it out. I mean, we've tried out an example already, and this is very trivial because it has the zeros and ones. So it shouldn't be very hard. And if you are a keen observer, you'll notice one thing. Here, most of the values are just 0 and 1. And here also it's 0 and 1. But then here, there are some terms which are negative. How is this possible? Because it's all positive numbers we're adding, right? So this image that you see here is after adding the bias, and the bias could have been a negative number due to which this happened. So yeah, this is what happened in the convolution layer. Finally, we are applying the activation function, which in this case is ReLU activation function. And in case you forgot what ReLU is, so basically in ReLU activation function, if x is greater than 0, y is equal to x. And if x is lesser than 0, y is equal to 0. So basically all the negative terms become 0, and whichever is positive just stays the same. So that's what happens here. A lot of zeros and just 2 ones. That's what we get at the end of this example. Well, someone has asked, please elaborate how we get the output matrix after applying the kernel. So I'm assuming you mean this is the output matrix. So after applying the kernel, the first thing we do is add bias to every single cell there is. And then we just put the activation function, which is ReLU, and this is what we get. Why negative? That's just what the bias was. It's like It can be anything. I'm just giving an example where the bias was negative, because of which the output became like this. I mean, that happens after learning, right? So yeah, moving on to the pooling layer. So pooling layer is to basically further reduce the dimensions by taking mean, max, min of a smaller group of cells. So basically, right now we have a 4x4 matrix, right? So we are going to make it a 2x2 matrix. What we are going to do is, from all four of these cells, like this is basically like the first two rows and first two columns, we are going to represent it by only one cell in the new matrix. Similarly, these four will have like this question mark, while these four will be represented by this cell, and the last cell will represent the bottom most square in this. So there are different ways to do it. We can take the maximum value, we can take the minimum value, or we can also take the mean value. And this is how it gets its name: max pooling, min pooling, mean pooling. So in max pooling, what we're doing is we're taking the maximum of these four values, which is 1, and we're going to insert 1 in this box. In this case, maximum is 0 because everything is 0. So this will be 0. And here again, it's 0. And in the last cell, it's going to be 1. So that's what we do. And that's what we got here as well. And if you, I mean, I just showed you, if you remember in the 4x4 matrix, there were zeros in like almost every cell except for two cells. So the minimum is obviously 0. So you just get 0, 0, 0, 0. Another potential option is mean pooling. And in mean pooling, of course, it's going to be 1/4 and 1/4 across the diagonal. And along the other diagonal, it's just 0 because everything was 0. We don't apply all of these things in each pooling layer. We usually just apply max pooling. And you'll be able to see why also, because min pooling doesn't, like, more often than not, you will be having zeros in almost every cell. Not every cell, but you might have at least 1 0 in a group of cells. And that will just make your entire image just 0, 0, 0. And that's not going to give you good results. So max pooling is what we generally use. So after max pooling, in this case, we just had 4 cells, right? It was 2x2. So now the input layer of the fully connected layer is just going to have 4 nodes. Initially, it had, I guess, 6x6, which was 36. So from 36, we came all the way down to 4. So that's a win. So now it's just a regular neural network at this point. There are going to be hidden layers, there are going to be weights, biases, and then an output layer. In case there are more than 2 outputs, then we can, of course, use a softmax. I hope you guys know what a softmax is. So yeah, that's it for convolutional CNNs. But the thing about CNNs is we're not just going to have like one convolutional layer, one pooling layer, and one fully connected layer. There are going to be like, it's going to be a combination of all of them. And sometimes like to different combinations, we give a specific name. Here you can see just an example of CNN. So there's a convolutional layer and then ReLU, which is part of the convolutional layer. Another convolutional layer followed by pooling, and then another convolutional layer, 2 convolution layers, in fact, and then pooling, and then 2 more convolution layers, pooling, and then a fully connected layer, which connects to a 5-way softmax, which classifies it into car, truck, airplane, ship, or horse. So we will be studying some architectures. So someone has asked about softmax function. So softmax function is just e to the power z, zi by sigma e to the power zi. And I is just the position of the node, basically. It's used when the output, there are more than 2 outputs. So it's like essentially, I think it was covered in one of the previous session, but still I just repeated. So that's what it is. So now we'll be going on to code implementation. I mean, before going to the code implementation, we'll just see some more basics that we need to know. We'll be implementing a VGG19 architecture, which is a form of a CNN. So what is VGG19? So the VGG stands for Visual Geometry Group, while the 19 just represents the number of layers which are there. So it belongs to Oxford University, and the aim of the VGG models was to understand how the depth of CNN models affects the accuracy when it comes to tasks like image classification and image recognition. So basically, the data set it was tried on had like 1,000 different uh, classes at the end. So we had to like classify it into 1,000 different classes. So that's the main reason why it was made. And at the time at which it was made, it was one of the best models. So yeah, so this is how the structure is. So out of the 19, I mean, there are 19 layers, right? Out of which 3 are the fully connected layers, while 16 of them are the convolutional layers. We aren't going to like count the pooling layers in this count. So basically, there are going to be like different blocks of convolutional layers, in fact, as you can see here. First, there are 2 convolutional layers, and then there's a max pooling layer, 2 more convolutional layers, a max pooling layer, and then it's supposed to be 4. There are 4 convolutional layers and then a max pool and then 4 more max pool, 4 more. This is how 16 comes up. And then there are 3 more fully connected layers. As you can see, the dimensions of the image keeps changing, and at the end it gets reduced to 7 into 7 into 512 when we are importing it into the into the neural network. Had we done it in the first step itself, we would have gotten like 224 into 224 into 64, which is a huge number. So before we can see how it is done, we need to understand how convolution happens in 3D cases. Like till now, every example that we covered was for a 2D example. So now we'll just see how it is done for 3D examples. So in 3D examples, I mean, usually till now, we can see that an image has, we say it has 6 cross 6 or 8 cross 8. So let's just call it height and width. So right now it has height and width. But now we're going to introduce a new concept called depth. And depth is basically the color channels in this case. So right now the depth is 3 because it's RGB. I think this was covered in the last class how the tensors look. Like supposing the image is just purely just red, then the red cells will have like 255, while everything the other layers will just have 1 and 1. And similarly for green, the green dimension would have like higher values, while everything else would be smaller. So we'll just get to how the convolutions are. So here you can see the depth is 3, while height and width is also 3. And in the output, however, the depth is only 2. So this is how it's done. So in this case, we don't have just a single kernel. You can assume it to be 2 pairs of 3 kernels. So here's what happens. You apply each of the 3 kernels. I mean, this is the first set, while this is the darker blue is the second set. So you apply the first set to all 3 layers, and then you apply the bottom set to all these layers. And then you add the input image of these 3 layers, and that becomes the first, you can say the first depth of the output, while the darker shade forms the second depth. I mean, I know it's confusing. Just stay with me. I'll go to the next slide. It's given more clearly here. So here you can see, the input depth is 2, while the output dimensions is just 1. Here's what happens. Here you just have 2 kernels. So what you do is you take the second kernel to the second dimension, and the first kernel is operated on the first dimension. And then we just add the sum of both to give the parent dimension. So I hope this slide makes it a bit more clearer. So, I mean, if you guys have any doubts, I understand it's a tricky concept. You can just put them in the chat. It's very similar to how a 2D is done, except there are multiple kernels and there's a new sum thing which was not there in the previous 2D convolutions. So this is how it happens. And in this also, we can just influence different parameters to have like different depth of the output. I mean, the different output dimensions. So let's see more about the VGG19 model. VGG19 consists of 16 convolutional layers and 3 fully connected layers. And in total, it has 19 layers. The input to VGG19 model is considered to be a 224 cross 224 RGB image. In some cases, it's possible that the image can be bigger than 224 cross 224. One of a popular way to trim it is to take the middle 224 x224 pixels. I mean, it's done in some cases, not necessarily in this. BGD19 uses 3x3 convolutional layers with stride is equal to 1 and padding equal to 1 in order to maintain the dimensions of the feature maps. So, I mean, we'll come to the dimensions part in the following slide. I'll explain it with a picture. After each convolutional block, a 2x2 max pooling layer with a stride of 2 is applied to reduce the spatial dimensions of the feature map by half. We saw this in one of the previous examples. Initially, it was a 4x4 matrix, and then it became 2x2. In that also, the stride was 2, if you noticed. I didn't mention this at that point. But yeah, a similar thing happens here as well. After the series of convolutional and max pooling layers, the resulting feature maps are flattened into a 1D vector and is given as input to the fully connected layer. The fully connected layer is followed by softmax activation, which gives the probability distribution. So flattening is, of course, using each pixel as an input node for the fully connected layer. And that's what we are doing. But it's better to pass it through the convolutional layers than directly do it. I mean, we covered these points at the starting. So yeah, now let's get to the dimensions. So the input dimensions was initially 224 into 224 into 3. It was 3. 64 is after the first layer. Like it's mentioned 64. Oh yeah, in this image it's better. So it's given 224 cross 224 cross 3. 224 cross 224 is the height and width. It's the number of pixels, while 3 is the depth, or you can say it's the input dimension. So in the first convolutional layer, what happens is the depth, the output dimensions is 64. We scale it up from 3 to 64. So that's what happens. We'll see how the hyperparameters are during the code implementation. And then we have the second convolution layer, part of the first block. In this also, it just remains 64. The input dimensions and output dimensions are just the same. It just remains 64 in both cases. And that's basically the first convolutional layer. After this, we have the next layer, which is, it's not a layer, it's max pooling. We don't count it in the 19. So the max pooling layer, of course, we saw it in the previous slide. There was a point. The 2x2 max pooling layer, the stride 2 is applied to reduce the spatial dimensions by half. So that's what happens here. You can see 224 cross 224 becomes 112 cross 112. It will still be 64. 128 is the result of the next layer. So it will basically become 112 cross 112 cross 64. 128 comes during the second block of the convolutional layer. It is basically made from 64 to 128. So that's how the architecture is defined. And in the second convolutional layer, in the second block, it is still maintained from 128 to 128 itself. Okay, so we have covered 2 layers and two blocks, and it has 4 layers. Now coming to the next layer, we have another max pooling layer. And you can see again, the height and width gets reduced by half again. It becomes 56 into 56. The thing is, after max pooling layer, the depth will remain the same. The depth increases during the next convolutional layer. So now there are going to be 4 convolutional layers. In the first one, it will change from 128 to 256 and then just remain 256 along the next 3. So, and then that is essentially the third block. Now moving on to the fourth block. Now we're going to once again go to a max pooling, and this makes it 28 cross 28 into 256. Putting it through the convolutional layer makes it 512 again. We repeat the same thing again, and at the end we get dimensions of 7 cross 7 cross 512. Basically, the thing is, after every max pooling layer, the height and width reduces by a factor of 2. But there is no effect on the depth or the input dimensions. And after the convolutional layer, in the convolutional layer, there is no effect on the height and width. It only affects the dimensions, which is the depth. So increasing it and decreasing it, it just depends on the architecture. In the previous class, you would have seen that when you define convolutional layer, you basically have hyperparameters which are input dimensions and output dimensions. That's how you define it. That's how it's done. So like at the end of the convolutional layers, you have a 7x7 x 512 dimensions object. So what we do now is we just flatten it and use this as inputs for the neural network. And the neural network is not just a direct one. We have two hidden layers as well. And the hidden layers have four. So yeah, I hope my screen is seen. You can just scan this and join. So this question is not directly related to VGG19, but it's just on CNN. So let's assume that you need to train your model and you don't have enough images. So how can you get more number of images? That's what the question is over here. You want to increase the number of images so that you'll get a better accuracy and reduce loss. But you have a fixed number of images with you. Using your resources, what is the best way to increase the data set? You'll get the attendance QR soon. And yeah, I guess I'll give you a couple of minutes for this question. Okay, so I've gotten like 50 responses, so I think I'll just show results. So yeah, majority of people have gone for data augmentation such as rotation, translation, and flips. And the next one is increasing depth of the network. And the third highest is reducing the batch size during training. And the fourth one is taking more images. Taking more images would be a good option, but then we need to use our resources, the resources we have to the fullest. So the answer, yeah, majority of you have gotten it right. It is data augmentation such as rotation, translation, and flips. Basically, we'll rotate it in various angles, we'll crop out certain portions, and because of this, we'll get a way larger data set using the existing number of images that we have. So it is pretty efficient. So yeah, now we'll move on to the actual code implementation. I'll just share my screen in a second. So yes, we'll just be going through VGG19 implementation using PyTorch. So VGG19 is just another CNN. So it's very similar to how you would implement a regular CNN, except the CNN architecture is is a specific kind. So of course, we need to do some imports before getting started with the code. We need torch vision.transforms. Well, like this is mainly like PyTorch libraries, and transforms is to apply some formatting to the images. Matplotlib is of course for plotting graphs for data analysis, and then NumPy is of course needed for everything. Torch.nn as nn is very important for the fully connected layer. Torch.nn.functional is for applying functions like activation function or loss function. And from PI import image, this is again for some image operations. So someone has asked a question related to the Slido question. Why can't we increase the data set by taking more pictures too? Well, you can of course take more pictures, but then it's like, I mean, it might not always be convenient, or you might not always be able to do it. I mean, you don't know what the data set is about, right? And using your existing resources itself, you're able to like multiply your data set by a good amount. So these are popularly used in like during image processing, and it's regularly used in CNNs. So yeah, let's get started. So we're just defining the transform first. We'll be converting the images to tensors using this, and we'll normalize the values of the of the of the tensors. And this is basically just represent the mean and the standard deviation. We are defining the batch size as 4. So that's the number of images that will be sent at a time. Having a lower batch size means you can have lesser number of epochs because it's a really small batch size. And now we're just defining the train set. We're going to use the CFAR10 data set over here. Note that in the original time, like in the competition for which VGT19 was made, there were like 1,000 classes at the output. Right now, we just have 10. So you will notice like there are going to be like some, you can say some interesting observations because we're using 10 instead of 1,000. So yeah. So yeah, we're just taking the train set, we're loading the data and then applying the transform. So this is how it looks after the transform. You can notice here there's a underscore over here. This is because in the train set, along with the image, there's also going to be a label. And right now we're just seeing how the images look. So you can see the dimensions, the input dimensions are 3, if you observe here closely. So yeah, we are once again defining the batch size for the train loader. And then we are, okay. Now we are defining the train loader. Earlier we had just imported the train set data. Now we are creating a train loader, which has to be done. Let's see how, when truck, this is a deer, this is a horse, and this is a car. So that's what this data set is all about. I mean, there will be 6 other clubs. So we finally arrived to the main part of the code, which is the VGT19 architecture. So, I mean, here the number of classes has been defined by default as 1,000. Will be changed 4. So let's see what's there in it. So the first block has a convolutional layer. And here you can see, you might have seen this function in the previous session during the code implementation. This is how the depth or the dimensions are changed. This is how the syntax goes, nn.con2d. 3 is nothing but the input dimensions. It's 3 because it's RGB. And now we are going to make it 64 dimensions. We're going to make the depth 64. And this is the kernel size and padding. And it's usually just 3 and 1 for all convolutional layers in VGT19. Now we are making a ReLU, and then we have another convolutional layer, and this time it's just 64,64, as it was mentioned earlier. Only in the first layer we are making the changes to the depth. That's how it was defined. And we have another ReLU here, and then we have the max pool. So in the max pool, again, the height and width will reduce. Initially, if you recall, it was 32 cross 32. So now it's going to be 16 cross 16. In the original VGT19, it was 224 cross 224 input, but here it's 32 cross 32. So now coming on to the second block, now we're once again increasing the input dimensions to 128. I mean, the output dimension becomes 128. Similar syntax, we're just changing the parameters in there. Kernel size and padding remains the same. We'll have a ReLU again, and then next convolutional layer and another ReLU, and followed by another max pool layer. So at this point, it was 16 cross 16. So here it's going to be 8 cross 8. So now we are further increasing the depth to 256, and we'll maintain it as 256 for the next 3 layers as well. And we have a ReLU between every single layer. And at the end, we have another max pool layer. Here it was 16 cross 16. At the end of block 2, it became 8 cross 8. And here it's going to be 4 cross 4 cross 256. 256 is the depth, and 4 cross 4 is height and width. Now we have the fourth block, and we have some more convolutional layers over here, and 4 of them to be precise. Here the depth is increased from 256 to 512. Honestly, it gets pretty repetitive. The same thing is just happening over and over again at different parameters. And the dimensions keep changing though, and most of the work here is, of course, done by the model. We just need to define it here. So similarly, at the end, we're going to have a similar block 5. And in this block, we don't even change the convolutional. I mean, we don't change the dimensions as well. It's just 512, 512 all the way. So this makes up the 16 convolutional layers. And of course, we have ReLU also at the end of each layers. And we also have our, I think, 5th max pool. And at the end of this max pool, in this case, the dimensions are going to be 1 cross 1 cross 512. If you remember, when I was explaining about VGG19, the initial images were 224 cross 224. So at the end, it was the dimensions were 512 cross 7 cross 7. However, here it's not going to be 7 cross 7, it's going to be 1 cross 1 because we started with 32 cross 32. So this was the convolutional layer and the pooling layers. Now we'll define the fully connected layers. So here the linear layer has, like, we're going to do flattening. It's going to like have 512 input nodes and 4096 hidden layer 1 nodes. And if this was the original VGG19, then it would be 512 cross 7, I mean, into 7 into 7, that many input nodes. However, here we're just going to keep it as 512 so that it doesn't throw an error. So we have a ReLU at the end of each layer, and we also have a dropout layer. I'm not sure if you encountered this before. Dropout layer is basically to prevent overfitting, and it basically randomly makes certain values 0 so that it isn't too over dependent on a particular value. So we have our first hidden layer and second hidden layer has 4096 nodes. Well, 4096, it was just decided like during the VGG19 architecture. It's like the entire model is kind of like a standard, you can say. So that's why it is. I mean, you might think that 4096 is abnormally high for this case, but you need to consider that in the actual competition, it's a very huge image, and proportional to that, it kind of makes sense. And at the end, we're going to have, of course, the linear layer, which is 4096 to number of classes, and number of classes in our case is 10. It'll probably be defined at some point later on. So yeah, we're just making the forward pass. Self.features is the convolutional layer. Flattening, of course, it's to connect the convolutional and fully connected layer. And finally, we have classifier, which is the fully connected layer, which is used for classification. So again, I'm not sure if you came across this before, device. So what we're doing here is we're making sure we use GPU rather than CPU in Google Colab. The thing is, convolutional CNNs are very computationally expensive, and even with GPUs, it takes quite a lot of time. And with a CPU, it will just run forever. So it's best to use GPU, and this is the process you use. And now we are just defining the neural network as an object. Net is equal to VGG19. Yeah, at this point, we're defining the output classes at just 10. And of course, we're also loading it to the device. The thing about GPU is you need to load the model as well as all the tensors to the device so that you can use the GPU, or else it'll throw some error. Here you can see it generated using device CUDA, which is basically, it shows that it's using GPU. And like regarding the GPU, it's pretty easy to make it. Just go to runtime and then click on change runtime type, and then you'll get an option to switch to GPU, and then you will get to use this. Yeah, so now we're just going to define the criterion and the optimizer. And this is the main training loop. We're just going to run it for 2 epochs. We had a very small batch size, so you don't need that many epochs. But however, at the end of this, you'll just see something which is kind of maybe weird. We'll just see it. So one important thing about the training loop is we are loading the input and label to the device so that we can utilize GPU. And we have optimizer .0_grad, and the forward propagation, backward propagation, optimizing, everything happens here. We also record the loss, and then at the end of every 2000 batches, we are going to be printing. We are going to be printing the loss, and then at the end, it'll finish training. So here you can see like a peculiar case. The thing is, at the end of every single 2000 batches, mini batches, the loss is more or less the same, 2.304, 2.303, 2.304 again. So, I mean, any guesses why it happens? You can maybe put it in the chat if you have like any guesses. But anyway, I'll just tell you anyway why it happens. The problem is with our data set. Our data set has only 10 output classes. Originally, in the competition, there were 1,000 output classes. So this model made sense for that. However, for our data set, it is just way too complicated. It has too many layers for such a small data set, because of which the learning doesn't happen. I'll just show you a simpler version, a simpler CNN using which you can work on even this data set. So this was just to show the VGG19 architecture and not necessarily get higher accuracy. So yeah, we'll just view the test data set and what accuracy came at the end. Since the loss is just similar, it hasn't really learned anything much. So you can expect a very low accuracy. So yeah, we're just checking what the predictions are. Moving on to the accuracy part, the accuracy is only 9%, which is it's really low. It's like maybe even if you just randomly guess the images, you might get a lower accuracy than this. Higher accuracy than this. But the low accuracy is mainly because the model is way too complex for this data set. I'll just be showing you another model. 1 second. So this isn't VGG19. This is just a random CNN basically. So like it's just mentioned VGG19, but this is a random CNN, but which is way more, way less complex than VGG19. Let's see what happens here. I've just removed every intermediate layer from VGG19. It just has the first layer where it kind of changes the input and output dimensions. And then there is, of course, like the linear fully connected layer as well. There are still 5 blocks, but then each block has only one convolutional layer and then ReLU and then max pool. Also, one more change is you can see that the dimensions of the hidden layer also changed here. It's something which is proportional to the size of the data set we have. We aren't putting 4096 because it would be like too much. Wait, so someone has asked a question. I'll just reply to that. Are the free GPUs provided by Collab efficient for CNNs? Yeah, it is. I ran it on the free GPU by Collab. The only downside to that is there's a limit. You can't just use it forever, basically. So yeah, that's the main problem. You can also use Kaggle. Kaggle also provides GPU for a limited amount of time. So yeah, this is our custom CNN. It's on the same data set. It has everything as the same thing, but the main difference is here the loss actually decreases because the model is not too complicated. And yeah, it starts from 2.303 and then goes all the way down to 0.358. Let's check the accuracy of this model. The accuracy of this model is 76, which is like a huge jump from what we had previously, 9%. So yeah, we've covered the code implementation of both a CNN and VGG19 architecture. So yeah, that was the end of my part of the session. Now Sriram will be covering transfer learning as well as ResNet architecture. So over to you, Sriram.
Guys, am I audible? Hello, am I audible?
Yeah, you're audible. Just a second. Before you start, I'll just share the attendance QR really quick.
Yeah, sure.
Like I'm sharing the attendance QR now. Like just a minute. Till then, you can just put any doubts you have in the chat. We'll answer them. So yeah, I hope you can see my screen. This is the attendance link. It'll be active for like 5 to 10 minutes. The thing about coding CNN is, see, the main thing about CNN is the architecture. It's the class in which you define the CNN. And honestly, like you would have seen major blocks of the code was just a single line, right? At nn.con2. And the main thing you're changing is just the parameters. You can always go through the documentation. That will make it easier for you if you have any difficulty coding. You can put any other doubts you have in the chat. We'll show the attendance QR for another minute or 2 minutes. The deadline for the hackathon is going to be Sunday, so you'll get 4 days, which is a good amount of time to try out your ideas. Just responding to someone had asked. So. Okay, so I think that's been enough of a short break. So Sriram will be covering transfer learning as well as ResNet architecture. So over to you, Sriram.
Yeah, so hello guys, I hope my screen is visible. Anish, it's visible, right? I'm not able to see the chat, that's weird.
Yeah, it's visible.
Okay. So good evening guys. So now we'll be looking at an important concept called transfer learning and a very important convolutional neural network architecture called ResNet, right? So what is transfer learning? So first I'll give you an intuition about what this concept of transfer learning is all about. So guys, we human beings, we are very good at applying transfer of knowledge between tasks, right? So what I mean is, when we face a new problem, so what is the first thing that we do? We try to understand what the problem is, and then we try to apply the knowledge that we already have gained, right? And which is relevant to the new problem, right? So when it comes to AI, we do the same. Transfer learning, it was introduced in the field of machine learning with the same idea. That is, the knowledge that was gained in some tasks, we apply to solve a problem to the related task. So basically, it is a machine learning technique where a model developed for a particular task is reused as a starting point. So the thing is, generally we start with random weights for all the parameters that we have, and then we train our model and we find those optimal parameters, right? So here we don't start from zero. We already have a pre-trained model which has been trained for a task A on a large data set, right? So we use the knowledge that this model has gained from that particular data set, and we take it into our model, which we are going to be using for the new task that we have. There is a problem at hand, right? So by using the learned features from the first task as a starting point, our model can learn more quickly and effectively on the second task. Because we are not starting from zero, the computational power required to get our new model working on task B will be lesser, right? Now, to give you a real life example, so you would see that the people who have mastered the task of skating, right, they can easily learn how to ski. So I hope you get an idea of what transfer learning is all about. So in the early layers of a CNN, what happens is the model learns the low-level features. What do you mean by low-level features? The features like the edges, the color, the texture, intensity variation, etc. Right. So such kind of features, they are not really specific to any particular data set. So no matter whether you want to detect a cat or a dog, right, you need to detect these low-level features irrespective of what is the data set that you have chosen or what the cost function is. So the idea is these features, these low-level features, they're universal across various data sets and tasks. So the features learned for one task can be effectively applied to another related task. So how does transfer learning work? Now that you have understood what is transfer learning, how are we going to implement it, right? So we start with a model which has been previously trained for a certain task using a very large data set. Now, why is this large data set important? Because only if you train it on a large data set, your model would have identified the general features and patterns, and which will be relevant to numerous other related tasks, right? So this pre-trained model, which has been already trained on some other task, you call it the base model. So there, what you do, you find some set of layers that capture the features which are relevant to the new task. That is a task that you have to build a model for, and the previous task, right? The task or the large data set on which it was trained. So we transfer those layers directly. So those layers of the pre-trained model, we take it directly into our model, and these layers you call freezing layers. Now, what is freezing layers? We'll be looking into detail in the upcoming slides. So after you have chosen what are the freezing layers and you have transferred some layers already from the pre-trained model, right? So then there will be the remaining layers. They are called modifiable layers. We'll be looking into what modifiable layers are in the upcoming slide. So those layers you will be fine-tuning, right? So you'll be training those particular chosen layers for the new data set that you have. The idea is basically to preserve the knowledge from the pre-training, right, which is relevant to the problem at hand, while enabling the model to modify its parameters to better suit the demands of tasks at hand. So we don't start from zero. We already start from a point where the model has already learned the general features which are both common to the previous problem and the problem at hand. So let's see how it will help in the upcoming slides as well. This is an example of transfer learning. So here you have a convolutional neural network which has been trained on a large data set like ImageNet, right? So ImageNet is a very large data set. It has around 1.2 million images with some 1,000 categories. So you have trained the CNN on this ImageNet data set, and you have some fully connected layers. And after that, you are getting the output. Basically, the images are classified into various categories like African elephants, snakes, lions, etc. So this model, now we are using it for some application in the medical field. Suppose you have some X-ray scan and you want to classify whether the patient, he is healthy or he has some viral pneumonia, he's infected by COVID-19 or something like that. So what you do is you select some layers, preferably from the top, preferably the top layers of the pre-trained model. right? Because these top layers will generally be capturing the low-level features, which will be common to your problem and the problem for which it was trained for. So you transfer those trained parameters directly, and then you train these fully connected networks over here, fully connected layer. This you will be training and fine-tuning for your particular problem at hand, right? So I hope now you understood what transfer learning, how transfer learning is applied in the field of machine learning and deep learning. So yeah, so what are freezing layers? So for example, you can see a convolutional neural network over here, right? So freezing layers means you are taking those layers directly from the pre-trained model, right? So those weights, you will be fixing it. You won't be training it again. And the remaining layers, they are the trainable layers. Now these layers you will be training and fine-tuning for the particular problem and dataset that you have. So freezing layers in transfer learning refers to fixing the weights of certain layers. So these two layers over here, you're going to fix them. You're not going to change them at all, right? So they don't get updated. No, these weights will be same as that of the pre-trained model, and you won't be updating these weights during your training. And these trainable layers, you will be obviously updating and fine-tuning for the problem at hand. Now comes an important question. So how do you determine which layers you need to freeze and which layers you need to train? Right. So this is an important question because it is very important to decide which parameters you should be fine-tuning and which parameters you should be fixing it from the pre-trained model. So how you decide that is, it's based on the relevance of the previous problem for which the model was trained and the model that you want to create for the problem at hand. So if there are more commonalities between these two, the number of layers that you will be freezing will be more. And if there is less commonalities, then you will just freeze the initial layers and not the rest of it. So what is the advantage of transfer learning? Why are we doing all this, right? So it speeds up the training process and decreases the computational power required. How does it do that? Because as I said, we are not starting from zero. We are starting from a pre-trained model which already has some weights. So some of the weights we are maintaining it as it is. We are not going to change, and rest of them we will be training and fine-tuning as per required. So that decreases the computational power, because otherwise you will have to train all the layers, and then the number of parameters that for which you'll have to find the optimum value, they will also be increasing, right? So the computational power will increase otherwise. The transfer learning, and it leads to better performance on the second task, right? Because it has already gained some knowledge from the first task. So all the knowledge that it has actually gained from the first task, so it can be applied for the second task as well. So it might lead to a better performance in most of the cases. And it also allows effective training with smaller data sets. Now, this is one of the most important use of transfer learning, because many times what happens is getting data set is not an easy job, right? So you would want to get your job done even with a smaller data set, and transfer learning allows that. So it allows effective training with smaller data sets. And yeah, due to its wide variety of applications in various domains like image classification, object detection, natural language processing, and medical imaging. So these are some of the domains in machine learning where transfer learning is applied. So now that you already learned about VGG19 architecture, where you had, I think, as per 16 convolutional layers and 3 fully connected layers, right? So does it mean that if you stack more layers, is your network going to do better? Right. So basically, is learning better networks as easy as stacking more layers? So if you want a better model, does it mean that you have to stack more layers? Like, if you increase the number of convolution layers, is your model going to do better? So that's the question that we have now. And yeah, so I hope you can see the QR. So this is a question for you guys. And the graph is shown over here. So this graph will help you to answer the question, which will be in the QR. Guys, I wanted to look at this graph in detail, because when I'll be sharing the screen for Slido, these graphs, at that time, it won't be visible. So I'll be waiting for 1 minute before I share the Slido screen so that you observe these graphs in detail. So basically, you have a 56-layered convolutional neural architecture, and you have a 20-layered CNN model as well, right? So this is the graph showing the training error of this 20-layered model as well as the 56-layered model, and this graph shows the test error. So based on these graphs, you have to answer the question which has been asked. So the question is why you have a lower test error for higher test error for 56 layer, right? Because you have stacked more layers. Now you have 56 layers. So you have stacked more layers, and why has the test error increased? So this is the question. I hope you guys observe the graph. So now I'll be sharing the Slido screen. Is the screen visible? Okay. Fine. So most of you are telling it's overfitting. Okay. And some of you are telling that it's more layers and higher the test error. Okay, fine. That's interesting. And some of you are telling underfitting, and some of you are telling vanishing gradient problem. Okay. Fine. I think the time is up. So I will explain the solution in detail in the coming slide. Yeah, so I hope you can see the presentation. So guys, okay, so first I'll tell the answer. The answer is it's clearly not overfitting. Right. Now, why is it not overfitting? It is because, see, if it was overfitting, see, what is overfitting actually? Now, I remember I had taken the session for regression models where I had explained overfitting and underfitting in detail. So in overfitting, basically, when you try to plot the graph in the graphical, I'm telling you the graphical meaning now. So to try to pass through all the points in the training data set. So when it tries to pass through all the points in the training data set, what happens is the training error will be less. So if what's happening here, if that is overfitting, then this 56 layer architecture should have had a lower training error than this 20 layer architecture, right? Because overfitting means what? It fits the training data very, very well. So the training error should be very minimum and testing error should be matched. So if the graph was like you have 56 layer over here and you have 20 layer over here, basically the training, if the graph had low training error for 56 layer architecture, but it had high testing error for 56 layer architecture, then you can suspect overfitting. But here clearly it is not overfitting. That's the first thing. Second thing, now underfitting. Now why is it not underfitting? It's clearly not underfitting because here you have more number of parameters, right? You have stacked more layers on over this, so it's not underfitting. Then the other option was when you have more number of layers, so lesser will be the test accuracy. Well, that's unfortunately wrong, and you will be seeing that VGG had 19 layers, right? So VGG 19 model that was now, it had 19 layers. Well, the model that we are going to discuss, that is ResNet, it's going to have 152 layers. So that has a better accuracy than VGG 19. So it's actually not true. So see, I didn't expect you guys to answer this question correctly. So it was just to make sure that you guys are along with me and you guys are understanding stuff. It's absolutely fine to get this question wrong. There's no problem with that. So the actual correct answer for this question is vanishing gradient problem, right? So yeah. So researchers, they had to tackle a new problem, right? When they tried to come up with deeper models. What do you mean by deeper models? By deeper models, what I mean is more number of layers, right? So the idea that the researchers initially had was when you stack more layers, the accuracy might actually increase, right? So at first look, this idea makes sense because on increasing the number of layers, you will be able to explore a bigger parameter space, right? So this led to the expectation of high accuracy. And that's what the aim of VGG research group was. So VGG research group, they started with VGG 11, right? That is, you were having only 11 layers, and they slowly upgraded their model and finally reached VGG 19, where they had very good accuracy. And after that, when they tried to implement deeper models, they found that their accuracy was actually decreasing than increasing. So now this made them wonder what is the actual issue, because it's clearly not overfitting as I explained earlier, because if it was overfitting, then the training error should decrease, but the training error was also increasing. What was the issue? Now comes a new problem called vanishing gradient problem. Now, what is this vanishing gradient problem, right? So when the network that you're training is very deep, so when it has many convolution layers and all, so the gradients where the cost function is calculated, right? So you know that in the backpropagation step, we'll be calculating the gradients of the cost function with respect to those parameters, and then we'll be updating them, right? So that's what backpropagation is. So when you do that, you find that these gradients are actually shrinking to zero. Now, why is this a problem? This is a problem because if the gradients are actually shrinking to zero, then the updation of weights and bias will not take only. I mean, weights, the parameters that you will have to optimize, right? So they won't get updated if your gradient is shrinking to zero. So and that happens because after you apply several applications of chain rule. So mainly the parameters in the initial convolution layers, right? So because the weights are not getting updated, there was no learning taking place. So you can see over here. So what theoretically was expected was the training error will decrease. But what happened is it decreased till a point. Okay, maybe you can say that VGG19 is over here. Right, and this was VGG11. So you had a high training error, and you slowly try to increase the number of layers, and then you reach VGG19. Training error or the testing error was also minimum. But when you started increasing the number of layers, the training error started increasing. Now it's clear. So the answer to the quiz question is the reason why the 56 layered architecture there in the diagram in the graph had a lower test accuracy than the 20 layer. It's clearly not overfitting because the training error for 56 layer came to be higher than the 20 layered architecture. So, and okay, now this is also a fact that when you have more number of parameters, there is a chance of overfitting. But in our case, it was not overfitting because you can see that the 56 layered architecture had higher training error, but it is indeed true that there is a chance of overfitting when you increase the number of parameters. And that was the reason why they were suspicious of overfitting. But when they plotted the training error, they found that it's clearly not overfitting. Now this shows you, so this shows you the timeline of computer vision architectures, right? So VGGNet was kind of came up in year 2014, and now the architecture that we are going to discuss, which is the backbone for various computer vision tasks, right? So that's ResNet, and we'll be discussing that. That came up in 2015. So ResNet in short is actually short for residual networks. It's a deep learning architecture which was introduced by a group of Microsoft researchers in 2015, right? So there was a very interesting paper which was released by a group of Microsoft researchers, and that paper is actually kind of a Bible for the deep learning architectures for the computer vision tasks that we have now. So it addressed many of the limitations faced by the deep architectures like the VGG models, right? So I think by now all of us have clearly understood that the main problem with VGG models was the vanishing gradient problem. So what was so great about ResNet? Now this is one important question, right? And how did it solve the problems faced by the VGG models, like the problem that we just discussed, that is the vanishing gradient problem. So this is the image of the, it's ResNet 34. So basically you have 34 layers, right? So we'll be discussing what is the structure of this what this architecture is all about in the coming slides. So now let's discuss the characteristics of ResNet. So in ResNet, you have something called residual blocks, right? So what is a residual block? A residual block, so this is a residual block. Okay, now I think this will give you a clear picture. So you have a convolutional layer followed by a ReLU, and then you have a convolution layer, and then you can see that a connection is coming from the input to the output of this convolutional layer, right? So these connections are actually called skip connections, right? So what are skip connections? We'll be looking in detail in the coming slides. So then I can tell you for now that these skip connections is what makes ResNet very unique and have a higher accuracy than VGG models. So this is the most important and the key feature of the ResNet architecture. Right. The rest is the usual. You have a convolutional layer followed by ReLU actuation. This was also there in VGG models. So this skip connection is the new thing that they have introduced in the residual blocks. And why is it called residual? That also we'll be discussing in the coming slides. So what are skip connections? What is the role in the architecture? How did it help ResNet beat VGG19? So we'll be looking into that. Skip connections. Right. So what are the skip connections? So these are basic. So what the skip connections does is it basically adds the input of the block right, directly to the output. Right. So it bypasses these convolutional layers and it bypasses the entire residual block and it connects the input directly to the output of the residual block. Now, how does this help in solving the vanishing gradient problem? Because now the gradient has an option to flow. Now you have, since you have added it with the input, now this helps in the gradient to flow backwards and it will not, the gradients will not vanish to zero, right? So this helps in solving the vanishing gradient problem and also ensures that the output, it performs at least as good as this input. So what was noticed was when you have many layers, the output was performing sometimes even worse than the input, which is definitely not what we want, right? So these skip connections, when you add this input to the output of the residual block, it makes sure that the gradient flows backwards and the model is not performing worse than the input. So this really helped us to increase the layers and make deep neural network architectures. Like ResNet architecture, it actually went up to 152 layers, right? So let's go to the next slide. So what was the motivation behind skip connection? Now the skip connection seem interesting. Okay, you are adding the input to the output of the residual block. Now, how does this, how did this idea even pop up, right? So neural networks, they are good function approximators, right? So that is, they should be able to easily learn the identity function. What is identity function? That is f of x equals to x. Now this is something which neural networks can learn easily. Now what happens is, because of skip connections, you are adding this easily learnable identity function to the output of the residual block. Now this makes sure that whatever your network is able to predict, it will be at least better than what the state of the input was. Now this also makes the training more efficient and it improves the generalization of the models, right? Yeah, and identity mappings, they help the network to focus on learning the residuals. So that's how the residuals, in the sense how much the output has changed compared to the input, right? So it basically helps us to helps the model to learn the residuals. So you have the input x and you have the output f of x after the residual block, right? So that's how you get the name residual block, because it helps in learning the change that output has undergone through the residual block. So now let's look at another important concept named bottleneck residual block. So this is a feature of deep ResNet architectures like ResNet 101 and ResNet 152 and all. So why was this bottleneck residual block introduced and how does this help? We'll look into that now. So you can see, first of all, that this bottleneck residual block, it clearly has a different architecture compared to the residual block that we already discussed, right? So here first you have a 1x1 convolution, right? And then you have a 3x3 convolution, and then again 1x1 convolution, and then as usual you have the skip connections followed by a ReLU activation. So why was this modification done? It was done because it helped in improving the efficiency and decreasing the computational complexity. How did it help in decreasing computational complexity? Well, that's a question for me to answer. I'll be telling it in the upcoming slides. So they achieved it by using a 3-layered architecture instead of the traditional 2-layer one, which was found in the residual blocks. Yeah, so this exactly is a bottleneck residual block. So suppose you have an input feature x with n feature maps tagged one over the other. So basically the depth of the input is n, right? So first you have 1x1 convolution, 2D convolution layer, right? Now the input feed, what it does is, so it's called the reduction layer, right? So it reduces the number of channels in the input tensor by a factor, usually half. So it makes sure that the output, the depth is n by 2, right? So input has a depth n, and the output of this convolution block is n by 2. I mean, the depth is n by 2. So how does this help? Now this is given as the input to the 3x3 convolution block, right? So the 3x3 convolution layer is also called the processing layer because that's where the main convolution operation is performed, and the features, the model is learning the spatial features. So now what it is doing, it is learning on the reduced number of channels, right? So initially you had n feature maps. So the depth was n. So you had more parameters to learn. Now you have only n by 2. So basically what is happening is you have reduced the number of channels. Now this helps in decreasing the computational power required. And now after that you have ReLU activation. Now the depth is n by 2. Now it's important that you increase the depth to n so that you can add, because you cannot add two things which are of different depths, right? So x had an input, it's an input which had depth n. So if you have to add that to the output, this also must have depth n. So to ensure that you have 1x1 convolution layer again, which is called the expansion layer. So basically what happens is you have a bottleneck. Now this 1x1 convolution, this reduction layer, it acts like a bottleneck. It doesn't allow all the feature maps. It decreases the number of feature maps to half. Then you have a 3x3 convolution layer where it's the processing layer where maximum learning takes place. It learns all the spatial features, and then there's an expansion layer where the is increased to n, right? So it expands the reduced feature map back to the original number of channels, and then what happens is there is an addition. And this addition is the same skip connection that we already discussed in the ResNet architecture, the same thing we have over here, right? So then it is added to input through the skip connection. Now this was introduced to deeper architectures like ResNet 101 and ResNet 150. All right. So guys, I think again it's quiz time. So another question for you to answer. You can slide the QR. Yeah, so I hope all of you have scanned the QR and tried the question. I'll share the Slido screen. Just a minute.
Hi, Sriram. Sorry to interrupt you. I think you're muted.
Oh, I'm sorry. I'm sorry. Thank you for stopping me. Yeah. Okay. Yeah. I'm sorry for that, guys. I apologize for that. I hope the screen is visible, right? Hello? Yeah, is the screen visible, Anish?
Yeah, screen is visible.
Okay, fine. Yeah. I'm sorry for that. Yeah. Yeah, guys. So let's look at the achievements of ResNet. I'm sorry for that. So ResNet 152, it was the top performer in the ImageNet contest, which was held in 2015, right? It had a very less error of, I think, 3.57%. It was 7% for BGG. So this demonstrated that it's actually possible to train very deep networks with over 100 layers, right? So VGG had only 19 layers. Now ResNet had 152 layers. And this all happened because of this important feature they introduced called skip connections, right? Because that's what solved the vanishing gradient problem. Now, ResNet's pre-trained models on large data sets like ImageNet are widely used for transfer learning. Now we'll look into that. So now we'll be implementing ResNet by transfer learning. So we'll be importing the ResNet 18 and we'll be using it to classify skin cancer dataset as malignant or benign. So we'll be doing that now. The idea of bottleneck residual block in deeper versions. So as I said, bottleneck residual block is something which they introduced in deeper versions like ResNet 50, 101, and 152. So it optimizes the computation efficiency and decreases the number of parameters. How does it decrease? By decreasing the depth, right? So if you had n in the input, it allows only n by 2 for the 3x3 convolution. So thereby it decreases the computation efficiency. I mean, it increases the computation efficiency and decreases the parameters, right? So yeah, so this shows various models and their depth and the accuracy that it had in the ImageNet contest. So ResNet had 3.57% error. So okay, not the accuracy, this was the error. Okay. And yeah, you could see BGG, it had 19 layers and the error was 7, right? So it's almost half for ResNet. So now let's go to the code implementation of ResNet. Right, so we'll be doing it using transfer learning. I'll stop sharing. I'll be sharing the collab in 1 minute. Yeah, so guys, I hope the screen is visible and I hope I'm audible. Yeah, so guys, so what we'll be doing now is we'll be implementing the ResNet 18 architecture on a skin cancer dataset to classify the skin cancer images as malignant. I mean, the images as malignant or benign. So is it like cancers or not cancer? So we'll be doing that now. So before we import the libraries, first what we are doing over here is we are from Google Colab, we are importing Drive and we are mounting it. Right. So this is a general practice. So while you deal with large data sets in Colab, right? For example, the data set that we are dealing with now, skin cancer data set. So what we do is we upload it to Drive, and this code called mount from Google Colab, so you can directly access the files from your Drive. So this is a very important thing when you deal with large data sets using Colab, right? Then you're importing the necessary libraries. You're importing Torch, you're importing OS, importing torch.nn as NN, importing NumPy, importing pandas, and all that. Right. So here you're so you're checking whether your Colab is connected to or your CPU, right? And here, so here what we're doing is we are first resizing the image to 24 cross 24, right? So 24 cross 224 cross 224. So that is the image size required for as the input for the ResNet 18 architecture. So we are doing that first. And then we are doing random resize crop. So we are basically randomly cropping a part of the image and resizing it to 224 cross 224 pixels. And similarly, we are doing random horizontal flips. So these are some of the data augmentation techniques, and they are generally used to increase the diversity of the training model, right? I hope that was clear from the Slido quiz of Anish. And then, yeah, so basically you're converting the images to tensors, right? So here you are normalizing the data. So this is done for training data, and here you're doing it for the testing, right? So yeah, so this is the link. So these links are actually the drive links for the dataset. So when you mount the drive and you give the links for the dataset like this, right? Yeah, so basically loading the data set. Yeah, so here I'm printing the data set size and the trained data size and the test data set size. So yeah, you can see that there are 2087 over there and 360 images for that's the test data set size. And the class name, so basically we are going to categorize the skin cancer images as, the images as malignant or benign. Yeah. So here we have just tried to display the images for you guys. So this is what, so here we have resized the image to 12,8 and then we have, this is the image that is shown to you now. So we are shown 4 images. Yeah, so now comes the important part, right? So here what we are doing is we are importing the pre-trained model. So here we are importing models.ResNet18. So we are importing the ResNet18 model and pre-trained equal to true, right? So it's already trained on a large data set like ImageNet, and we're importing that ResNet18 model over here, right? So when if I give model, then you can see what the model is actually over here, right? So you have a lot of convolutional layers, and this is the architecture of ResNet18. See, basically hard coding an architecture like ResNet18 or ResNet50 is going to be pain. So that's where transfer learning comes very helpful in that way also. Right. So yeah, so you can see that yeah, so the num features is equal to model.fc.in features. So basically the number of features. Now that what you have done is you have loaded the ResNet18 as it is, which is already trained on a large data set. Right? So you have loaded the ResNet18 model. Now we have to freeze the layers that we want to freeze, and the rest of the trainable layers, we should be training it. Right. So you can see that. So what we are going to do now is we are going to freeze the convolutional layers, and only the fully connected layers we'll be training now. Right. So you can see that for the fully connected layers, the in features, right, the input features, the depth is 512. So we are defining the num features. Now what we are doing is we are taking the convolutional layers of the ResNet18 as it is, and the fully connected layers we will be introducing and we will be training it. Right. And you can also see that the out features for this fully connected layer for this data set is 1000, right? Because ImageNet had 1000 output categories. But the data set that we are dealing with now is skin cancer data set, and you have to classify those images as malignant or benign. So the out features are going to be 2, which we'll be correcting it. So this is what we'll be doing in the in code snippets. So so the number of features on the pre-trained model, right? So you have the features as 512, right? That's what you saw over here. Now, yeah. Now this is a very important step. So here what you're doing is you're giving parameters dot request grad equal to false. Why is this important? Because you don't want those parameters in the imported model to be trained, right? The idea of giving this false over here is because you're going to fix it. You're going to freeze those layers, and then you will be training the fully connected layers that you'll be fine-tuning only those layers for the problem at hand, right? So here you have what you have done is you have model.fc equal to nn.linear num features, comma 2. So basically what you're doing is you are going to add the fully connected layer to the imported model, right? So you have imported the 18 layers, and now you will be adding these fully connected layer, and then you will be training it. So basically those fully connected layers parameters will not be updated because you have given the grad equal to false. Now model equal to model.toDevice. So you are uploading it to the GPU. And this shows what is the model now, right? So yeah, now you can see that you have imported the convolution layers of the pre-trained model, and then you're going to train the fully connected layers, right? So the cross entropy loss is being taken as the loss function, and then SGD with momentum is the optimizer that you are taking. So here you are seeding, and yeah, so this is the training loops. The number of epochs that we have taken is 30. So what we'll be doing is we'll be training it, and after every epoch we are printing the training error and the testing error, right? Yeah, I hope you are familiar with this now, I think after these sessions. So here you can see that I have implemented it for 30 epochs. So after every epoch, we are printing the loss, we are printing the accuracy, and also the time taken. So we have done it for all the 30 epochs. Right? Yeah, so now here what we are doing is we have the y predicted and y true. Right. So basically, we want to plot the test error and the train error. So that's what we are doing over here. So yeah, so basically plotting the test error and train error, and you can see that we initially started. See, because we had a pre-trained model, we initially started with a model with some 74 to 71% test accuracy, and then finally we can see that our model has saturated with something around 82% accuracy. Right. I think this was clear from here as well. So here you can see that the test accuracy was 82.42 for the test, and train is also 80.7. So 78. So it's a pretty good accuracy, I would say. And since it was a classification task, here we have plotted the efficient matrix. So this is a very good parameter when it comes to performance metric, when it comes to classification tasks. So here, there's also a classification report given to you with the precision in both malignant and benign, right? So yeah, so this kind of comes to the end of the code implementation of ResNet 18 on the skin cancer dataset to classify it as malignant or benign. So guys, any doubts on whatever has been discussed till now, you can either raise hands, so we'll be giving you an unmute option, and then, or else you can put it in the chat as well. Yeah, I will also be displaying the attendance QR now for those who couldn't scan it the last time. Okay, so I think somebody has asked out regarding skip connections. So what skip connections does is basically you so you have okay, wait, I think after this attendance QR, I'll be explaining I'll explain skip connections in a bit more detail so that you understand better. Yeah, so I'll explain skip connections once again. Yeah, so I hope you can see the skip connections. So basically what is happening is you're adding, so before what used to happen in BGG models was you had some convolution layers, you had an activation, then you had again some convolution layers, and then it goes on, right? So what happened was after some point, the output was performing or output was actually worse than the input that you gave to the model. So skip connections, what it does is, so basically it adds the input to the output. Now it's easy for the model how to learn to just copy the input and give to the output, right? So the idea was basically the model will be easily able to learn how to get better at the task rather than getting worse, which was outside, because at least it will be able to copy the input as it is and add it to the output, right? So in that way, you kind of make sure that your model is not doing worse than what it was doing before. I hope this gives you an intuition. Mathematically also, it's probably visible that you're adding f of x plus h, and it's easy for the gradients to flow back towards the top layers where that's where the gradients are actually vanishing or shrinking to zero, right? So when you do back propagation, when you calculate the gradients, these skip connections on adding the identity function make sure that the gradients are actually not shrinking to zero. So that was the idea of bringing in skip connections. So basically, the neural networks, since they're good function approximators, they are very good at learning identity mapping. Right? What do you mean by identity mapping? Just f of x equal to x. That's all. And when you add, so operation that you're doing is adding. That's why I always emphasize adding. That's nothing more than that. I hope you guys understood what skip functions are in a better way. Okay, so somebody has asked gradient vanishing brief. Okay, so what was observed was, see, in VGG models, right? So when you're in VGG architectures, what their aim was actually to see how the test accuracy changed when you increase the number of layers, right? So in the case of VGG, they initially started with 11 layers, and then they slowly increased the number of layers, and then they reached 19 layers, right? And after that, when they tried to increase the layers, what happened was they encountered this vanishing gradient problem. So the gradients of this gradients that you compute, right? So basically what you do is you do dou J by dou W, right? I think now you will understand better. So this was shrinking to zero when you calculated the gradients for the parameters in the initial layer. Why does that happen? Suppose you have a gradient as 0.9. Okay, that's for the last layer. When you multiply 0.9 many times, right? You can see that the gradient is actually shrinking, right? So I hope now you get an idea why I say the gradient is actually shrinking. So it was observed that when you mathematically computed the gradients for the layers, and then when you went up, because in chain rule, what you do is you just multiply the gradients, right? One over the other, and you get. So when it was multiplied, it was shrinking to zero. Basically, it was getting smaller and smaller and smaller. So due to chain rule. So that was the actual issue when they tried to increase the number of layers. And these skip connections, they kind of solved that issue by having an identity mapping and not allowing it to vanish to zero. So basically, see, the problem is if the gradients become zero, if they shrink to zero, then your parameters are not going to get updated. So it's going to remain as it is, and there is no learning going to be taking place. So in order to make sure that they don't shrink to zero, what we did is they introduced a new idea called skip connections. So they make sure that the gradients are not becoming zero and the parameters are getting updated. Yeah, so I think I have clarified the doubts. Yeah, so I think, guys, that's all for today's session. I hope you guys understood the basics of CNN and various architectures like VGG19 and ResNet. Hope you guys enjoyed today's session. And as already mentioned, you won't have an assignment for this session and for the next session. And you will have the Kaggle competition, which is compulsory, right? So all the best for the Kaggle competition. Yeah, so that's all for today's session.